In the last video I made on my 8-bit breadboard CPU, I talked about the program counter and how it links up to the 16-bit address bus. Since then, I've connected up the ROM and RAM to the address bus, as well as building the circuit that will select between them and other devices. I've also built the instruction register, which holds each instruction as they're executed, and connected these two devices to the main data bus, where it can be sent around the computer. The first device connected to the address bus is the RAM, which holds most of the data used in this computer. Since this is a Princeton architecture, it holds both instructions and data, as opposed to a Harvard system like Chump, where there are separate components for each. As I said in my previous video, this is a 32 kilobyte RAM, although somebody pointed out to me on the last video that I could have easily gotten two of them and selected between them automatically. So I might do that at some point, although 32 kilobytes will do for now. The second device connected to the address bus is the boot ROM. This will hold a small program that simply tells the computer how to read in a program from an outside source and program it into RAM where it will be properly executed. And it will always run before anything else does because it sits at the very top of addresses, starting from address 0. The way these are selected between is fairly simple, and it's done by this part of the computer. The ROM sits in the top 256 addresses, and so it can be selected using the NOR of the high address byte. And that's what these wires are doing here, taking out the high address byte to decode them. If the high byte is all off, the ROM must be enabled because you're in the first 256 addresses. The RAM takes up the first half of the addresses except for the part the ROM sits in, so by just checking the high bit and checking that you're not in the ROM section, the computer can know when to enable the RAM or not. And then finally, when I/O devices are connected, which they aren't right now, and that could be a screen or it could be some sort of input, or it could just be a device that will hold a program to be programmed in, like a bigger ROM. But when those I/O devices are connected, they'll sit in the very bottom of the addresses, taking up 256 addresses each. Although it'll be rare for any I/O devices to actually use all 256 bytes of their address space, this gives an easy method for selecting between them. And that's that if the high 6 bits are all off, then you know you're in the area of addresses dedicated to I/O. Then, simply decoding the next highest 2 bits gives you 4 unique signals for 4 unique devices. And of course, that could be changed for more or less devices with the number of decoded bits. You could decode 3 for 8 devices, 4 for 16 devices, and so on. But I plan on doing 4. When enabled, or always as of now because I don't have any control signals yet, the instruction register will take in a value stored at the address on the bus to be decoded. This register always holds the current instruction being run and feeds into the address pins of the control EPROMs here, where the instructions can be decoded into control signals, which flip switches all around the computer. And that's how the computer knows what each instruction means. The next step in building this computer will be to program these EPROMs and begin adding instructions to give this computer some function. Right now, I've just put some example code, or not example code, just some dummy bytes of data here in the ROM so you can see them appear on the instruction register. There they are. 1, 2, 3, 4. And that's what the whole thing looks like right now.